Good afternoon, everyone. I'll first thank the organizers for such a wonderful conference and giving an opportunity to present our work. I'll talk about revealing local spinous effects by connecting the Lieb-Robinson bound and multivariate entanglement in multi-qubit weighted graph states. So I'll start with the motivation, what are graph states and what are long-range systems, then how we incorporate both of them to construct weighted graph states, and the dynamical quantities. We'll first is mutual information, Lieb-Robinson bound, and the multipartite entanglement, and I'll then finish with conclusion. So starting with graph states. So if there's a poly group, and if we take a abelian subgroup of the poly group, the states, these are stabilizer, and the stabilizer states would be the states which have +1 eigenvalue of them. And graph states are a subset of stabilizer states in which the stabilizers can be represented by uniquely represented by a graph. And these are resource for measurement-based quantum computer that was shown by Rossendorf and Brigel in one-way quantum computing and has been experimentally constructed in photonic systems. Cluster states is now a subset of graph states where the graph is a lattice with interaction of edges, and the complete protocol of performing universal gates in cluster states was given by Rossendorf, Brown, and Brigel. These states can be generated either as a ground state of a Hamiltonian, which is just sum over of the stabilizers, negative sum of the stabilizers, or dynamically by starting with a plus state. So in qubit case, where there are only two levels, the plus is just sigma x eigenstate with a +1 eigenvalue. And if we start with n copies of it and evolve it with a Ising chain, at t equals to pi, this becomes a control Z operation, and the resultant dynamical state is a cluster state. And people have shown that this is a symmetry protected topological phase, and such kind of states have a computational power for measurement-based quantum computation. So we can generalize this Hamiltonian to a multi-qubit Hamiltonian, in which the summation now goes to the number of levels, and the cluster state is at now 2 pi by d. And the use of these states for computation was given by Zhao and others, and recently have been experimentally done in transmon qubit and photonic systems. Now I'll talk about the long range system in which, in physical sense, the different quantum systems interact on nearest neighbor, but they also interact with other quantum system far apart, but the interaction strength decreases with the distance, and this alpha is called the fall off rate. There's been interesting studies which has led to a recent RMP, and this shows that these models can also be experimentally simulated in single mode or multi-mode QED cavity systems and trapdyne systems. These the properties of these systems vary drastically from the short range systems, and Goshkov has shown that there's a bound on the entanglement growth. There are critical phases recently transport in long range systems by Katha and Manas. There's thermodynamics. Our group works mainly in the dynamical properties, metrology, and recently they have shown the benefits of long range interactions in battery and state transfer. Experimentally, this was first introduced by Chirac in the 2004 paper, Trapdynes, and then has been seen in exclusively with Rydberg atoms, resulting in a review by Klaus Maumer. And also, these are the recent paper, this last month papers, where they show that even the ZZ interactions which I'm talking about are implemented on a superconducting qubit. Now, how to incorporate these two in a weighted graph states? So these are, if I'll say these are the computational bases, which are the sigma z, which are the SZ eigenstates. So the Hamiltonian is still the Ising Hamiltonian of this form, but the interaction strength now decreases as the distance. So this is for there are two dimensions. One is local spin dimension, which is small d, and a capital D, which is spatial dimension. So the spatial dimension is encoded in the possible values of R the system can take. And if we start with the same plus state, which is now the superposition, so the plus tensor n is the superposition of the eigenstates, coherent superposition of the eigenstates of the Hamiltonian, and evolve it similarly, we get a weighted graph state with the corresponding weights. And weighted graph states has been studied in qubits by Maciek way before, and has been recently seen by Anil Shahji and Chandan Mahato. There's a nice review of weighted graph states. So I'll now move on our work where we compute the dynamical quantities. So we first compute the mutual information which quantifies the total amount of classical and quantum correlations in the system. This tells us also about the localizable entanglement in the structure, the bound on the localizable entanglement, and we first see in the small distance from the qubit, like the mutual information is between the qubit at site 1 and site r+1. This is for 1D open chain. Now for very small alpha, the mutual information remains local in the sense in very small r for small times only, and moves on to larger r for instantly, whereas for large values of alpha, so alpha tends to infinity is the local limit. It is just the nearest neighbor interactions. So the mutual information remains local for a large time. So we see this even in for d equal to 3, but there's a qualitative difference. We try to quantify it using the average of mutual information, and we see that this figure, that is for small alpha, no matter the r, it will go off exponentially. It will go off with power law, whereas for high alpha, for nearest neighbor regions, it will be there, but at large regions it will again fall off power law. So if you want to see this effect, like the turn, we fit this graph in a quadratic sense for small r1 to 10, r2 to 10, and we do see the change in behavior at exactly log 2d. This is more of heuristic, and I'll move on to Lieb-Robinson bound, which will show more this behavior more concretely. So Lieb-Robinson, bounds are the bounds over change in perturbation. So there's an operator at x, and the change in perturbation at a site y, and what is the change in the evolution of ax, of the operator ax, is given by this. In the first order of the perturbation, this is given by a operator norm, which was happily introduced in the last lecture as well. So we take two norms. The good property is also the self-dual, and these have been studied in non-relativistic quantum mechanics to show that in short range there's a linear light cone, and has been extended to long range to show power law light cones. In a recent work, they have summarized for general Hamiltonians and proved that for commuting Hamiltonians, which is our case as well, for commuting Hamiltonians outside the light cone, this commutator, which is the same as this, is scales as t by r to the power alpha, which we also find. And we were able to compute for L2 norms, using L2 norms for a general operator A and B, optimizing over operator A and B to get the maximum value of this bound. We get, it's nothing, just the projector over plus plus. So this tells us that there is a change in probability of clicking plus plus in the measurement due to small perturbation. That is change in trajectory of plus plus in a system starting with any state. So we find that it gets maximum at these particular times. So if we just take n equal to 1, this is the first maximum, and which satisfies this equation. And outside the light cone, we do get t by r to the power alpha. Note that these are spatial dimension D-independent results and does not depend on periodic boundary as well. So if we compute the velocity of this wave packet, this is not a wave packet, of this packet of the bound, So we get the velocity which scales as some exponent of t, and this shows that no matter the spatial dimension, for alpha less than 1, the velocity will increase with time as an accelerating, and for alpha less than 1, alpha greater than 1, it will decrease with time as an deaccelerating. So this gives a dynamical non-local region, which means that for high time at high sites, there will be a transfer of information. Now for the next, for the long range effect, in 1D system, for the first long range effect comes in our next nearest neighbor, for which r equal to 2, and putting r equal to 2 here, we do get back the alpha equal to log d statement, and here n and d has to be co-primes. I'll finally move on to the multipartite entanglement, which we measure by our distance-based measure, generalized geometric measure. This was introduced by Tuesday and has been used to compute multipartite entanglement in graph states way back. This form was given by Aditya and Ujjwal to compute. They show that for pure state one can compute by maximizing over all the bipartitions of the state A, and lambda are the Schmidt values, and have been extended to mixed states to show that there are multiple quantum phase transitions, and recently again to show the non-classical correlations. So since there's a maximization over all bipartitions, we first see for small system sizes that from which bipartitions does the GGM comes from. So we see that for major part of the profile, it comes from a single site density matrix, which in periodic chain is, you can take any site, but in open chain, it comes, the edge one is the one which gives maximum, and this change reduces with system size. We found that this reduces exponentially because there's a log scale in the y-axis with system size. That means if we take large enough system sizes, the multipartite entanglement in weighted graph states comes from the single site density matrix at the edge. This helps us to compute GGM. So if we first look at for nearest neighbors, and the solid line is for open boundary and the dotted line is for periodic boundary. So periodic boundary is all, the GGM in the periodic boundary case is always greater, but it is maximum only at 2 pi n by d. Again, n and d are co-primes, which can be seen specifically in n equal to d. So d equal to 10. So there are a lot of spikes, but the maximum occurs at only n equal to 1, 3, 7, and 9. And the maximum value is 1 minus 1 by d. So to see the long range, the effects of long range interactions, we do see that there are other discontinuities. So this, first of all, this is the differential with respect to alpha, and the y-axis is in log scale. So the periodic boundary condition is smooth, but changes its signs. Whereas in open boundary condition, there's a clear discontinuity. There's other discontinuity as well. So we also look at the difference from the maximum value. So this does show the same equation shown by the Lieb-Robinson bound, that the maximum occurs at when r and t satisfy this equation, and the vertical lines are for r equal to 1, which is nearest neighbor, and different n, whereas the long range interactions comes in the parabolic loci of this. For n equal to 2, r equal to 2 type cases, they fade out in the large alpha limit, whereas these does not. So this way we can say that states at these particular times are interesting because they have the properties of having a maximum multipartite entanglement and spread of correlation. So to conclude, we represented weighted graph state as a dynamical state of long range interactions. Dependence, we found dependence of information theoretic quantities on local spin S system, and the Lieb-Robinson bound gives a spatial dimension D independent relationship, giving a dynamical non-local region. The same relationship is satisfied by the multiparty entanglement, which is an H property in WGS. And the lingering question is, are these dynamical states symmetry predicate topological order in the long range sense? So this is the team. This work was done with Devkanto, Preetham, and Aditi. And this is the this is group in 2004, our group in 2005, and group with some previous members. And finally, the more or less complete group of QIC at HRI. So Manavda is here, Himadrida was here, Shubhanada is here. So, thank you.
Go ahead, do you have a microphone next to you?
Yeah, so I just had one question. So how do you define light core in such spin systems?
So this is a polynomial light cone. So you can use some definition that it goes some fraction of the maximum, or we have taken it as a maximum, because it will decrease polynomially outside the light cone, and even for general Hamiltonians, it decreases polynomially for even high alpha. This is polynomial decrease, this is polynomial decrease, this is polynomial decrease.
But how exactly do you define the light cone?
We define the maximum value of this commutator, the yellow region in this case. So this is the light cone in long range system. This is either hyperbolic or parabolic.
Okay, so for alpha equal to 0, it will be like
Alpha equal to 0, it will just
flat. Okay.
flat.
Okay. Yeah.
So the velocity will go as 1 by alpha. It will not be flat, but it will be very fast, where it will go by, sorry, 1 by 0, which is infinity. So it will go flat. Yes.
Okay, sir. Yeah. Thanks.
Other questions? I have a small one. You motivated the study by stabilizer states, and those featured Pauli matrices. And then you switched to spin S or d-dimensional systems instead of qubits. Does the stabilizer picture survive here?
For the nearest neighbor case, in qubits it does, which was, I can't refer to this work specifically, this work. And they have also been shown that they, even in qubit system in nearest neighbor cases, they are symmetry protected topological state. They are general, they are non-invertible symmetry protected topological states.
I see. Thank you. Any other questions? Then let's thank Keshav.